All right, so this is on the 11.1, 11.2 homework. It was due last week, but this question was still pretty hard, so I want to make a video on solving it. The integration especially came out to be kind of rough. So the question is asking us to find the coordinates of the centroid of the curve that's given, where you're given the curve in parametric form. I went into Desmos here and graphed it. So e to the t cosine t, e to the t sine t for your x and y coordinates from 0 to pi for your parameter. It makes this graph. So I know it doesn't look like it, but here it's starting at 1, and then it's going, and it's kind of looping back behind itself, back this way. Okay, so we are not finding the centroid of like an area like we had done in the past. We're finding the centroid of just this line as if it was like a wire or a paper clip or something that had been folded all out. So just looking at it, the centroid is going to be somewhere around here. And keep in mind that the centroid does not have to be on the wire itself. It may be impossible to actually balance this wire anywhere on the wire, but the centroid will just be out in space somewhere, the center of mass of this wire. Okay, so with all that said, let's just kind of jump into all the math. Remember, when you're finding center of mass stuff, you need to find those moments. So we have the moment sub x. The moment sub x is going to be the integral of the y wiggle. Find my wiggle here. So y wiggle dm. We have the moment sub y. Moment sub y is the same exact thing, but this is going to be the integral of x wiggle dm. And the only other thing that you have to worry about is the total mass itself. Total mass itself we get just by integrating over that dm. Remember the dm, little dm, geez, stop it, word, dm. This represents the differential of the mass. In other words, when you take that wire and you split it up into those infinitesimally small pieces, this is the mass of just one of those tiny little pieces. Okay, to find this mass, you have to take the density and then multiply that by the length of each of these infinitesimally small things. We're just going to let the density just be 1 because we're trying to find the centroid, and the definition of a centroid is for it to have a constant density. We might as well let that be 1. This little length, remember, this is the differential of the length, and that is something that we did when we were trying to find arc length. So this dm is going to be 1 times, and then the differential of the length is going to come from the Pythagorean theorem. It's going to be the tiny little x, so the derivative of x squared, plus the derivative of y squared. Okay, so this was just a definition that we saw before. This represents that tiny little distance of an infinitesimally small thing. This is not the second derivative. I know I wrote that funny, but the first derivative squared, second dy dt squared. Okay, so let's go ahead and figure out what that's going to be for our example. And this was kind of ugly. So we need to take the derivative of x and then square that. But we have this e to the t cosine t, which means when we take the derivative, we're going to have to do product rule stuff. So we're going to do the first e to the t times derivative of the second, which is sine t, plus the second cosine t times the derivative of the first, which is e to the t. Okay, so and then that is all going to be squared. It won't do it for me now. Oh no. There he goes. Okay, and then the same thing for the y. So we're going to take the derivative of the y. So first, derivative of the sine is cosine, plus the second sine times the derivative of the first, which is just e to the t. That's all going to be squared as well. So unfortunately, we're going to have to actually square out these binomials here. So squaring this, just pretend there's 2 of these side by side, and we're going to FOIL it all together. So we're going to do this e to the t negative sine t times another e to the t negative sine t. E to the t times e to the t is e to the 2t, and then negative sine times negative sine is sine squared. All right, then you're going to multiply the inner and the outer, which is just multiplying these 2 terms together, and there's going to be 2 of them. So we're going to have e to the t negative sine t times cosine t e to the t. So again, we're multiplying e to the t times e to the t, which is e to the 2t. There is going to be a 2 out in front because you're going to have 2 of these combined together. And then we're multiplying a sine t and then cosine t as well. And then plus, finally, the last term multiplied by itself, we'll have an e to the 2t and then a cosine squared t. All right, so this was just foiling out the first parentheses. We also have to foil out the second parentheses. So just real quick, e to the 2t, and that's going to be cosine squared t. And then plus, there's going to be 2 of the middle terms, so e to the 2t, cosine t, sine t. Plus the last term, e to the 2t, sine squared t. Okay, still all under the square root here. All right, now a lot of this stuff is going to disappear. So we have this negative 2 e to the 2t sine t cosine t, which cancels out with this term over here. So these 2 terms just disappear. Then we have this. We have an e to the 2t sine squared plus an e to the 2t cosine squared. If I factor out the e to the 2t, I end up with sine squared plus cosine squared, which is just 1. So underneath my square root here, I'm factoring out that e to the 2t, and then the sine squared and the cosine squared just go away. We have another one of these here, an e to the 2t cosine squared, and then over here an e to the 2t sine squared, which is going to give us another e to the 2t. All right, so just adding these together and then taking the square root. So we're going to have a square root of 2, and then when you take the square root of e to the 2t, you just get e to the t. All right, so this is our dm value, square root of 2 e to the t. This lets us find our total mass, just real quick, because this one's pretty easy. So our total mass is going to be integrating over our parameter from 0 to pi of this dm value, which is the square root of 2 e to the t dt. So this has antiderivative square root of 2 e to the t. All right, and then we're going from 0 to pi. Okay. All right, cool. So when you plug in pi into this, you're just going to get square root of 2 e to the pi. Minus, when you plug 0 into this, you're just going to get square root of 2. And unfortunately, you're just kind of stuck with it like this. You could factor out the square root of 2 if you really wanted to. I don't know if it's going to help too much, but you might as well. So square root of 2 e to the pi minus 1. All right, so that is the total mass of my wire. Now we have to do the hard ones, and that is going to be those moments. Let's do moment with respect to x first. So the moment with respect to x is going to be another integral, still from 0 to pi. Okay. Remember that the moment sub x, just scrolling up here, was the y wiggle dm. X wiggle, y wiggle represents the center of mass of each of the tiny little strips. But because our strips that we're talking about are just these infinitesimally small little links along the curve, my x wiggle, y wiggle is just going to be whatever location we happen to be at during our integral, which means that the x wiggle, y wiggle is just substituting in the parameter in for whichever variable we're talking about. So the moment sub x y wiggle, we're just going to substitute in e to the t sine t. And then we still have to multiply that by that dm, which is the square root of 2 e to the t. Sorry, I had to pause the video there. Okay, so yeah, sorry, I had to pause it twice now. To get through this integral, we're going to take the square root of 2 out. And then we're going to leave us with the integral from 0 to pi. We'll multiply the e's together, so it's e to the 2t. We have a sine t and then a dt. Okay, to do this integral, we're going to have to do integration by parts, and we're going to have to do integration by parts twice. I wrote it all on a piece of paper here, so I'd make sure I wouldn't mess anything up. Let's not forget that the square root of 2 is there, but we're going to add that back in after the fact. So let's just worry about figuring out, and we don't even want limits here. Let's ignore the limits for a second as well. Let's just try to find the indefinite integral of e to the 2t sine t. We'll plug the square root of 2 back in after the fact, and we'll plug in the limit 0 to pi in after the fact as well. Okay, so integration by parts, we want to set up the u and we want to set up the dv. It really does not matter which one you set to be which. I'll just go ahead and do it in the order it's in. E to the 2t for the u, my dv I'll let be sine t dt. Okay, You also have to figure out the du, so that's just the derivative of e to the 2t, which is 2e to the 2t. And then the antiderivative of dv, the antiderivative of sine is negative cosine. All right, so now we do the integration by parts. I'm just going to go ahead and copy down this left-hand integral. We're going to need that because we're going to have to use that after the fact. So this integral is equal to the integration by parts, which is u times v, so negative e to the 2t cosine t, minus the integral of v du, so negative 2e to the 2t cosine t dt. Okay. So that's just one iteration of integration by parts. We can clean this up a little bit. We have a double negative, which we can take, and we can pull this 2 out of the integral as well. I'm just going to go and do that as we go. So now another integration by parts. Pretend that this negative 2 is pulled to the front. I'm going to do the same u. U could be e to the 2t, but this time my dv is going to be cosine t dt. All right, we have to also have to find the du part, so 2e to the 2t, and then v would be the antiderivative of cosine, which is a positive sine of t. Oops, no dt there. There should be a dt here, though. I don't think I did that for this one up top, though. Should be a dt there, just to be official. All right, so now we have to be very careful about plugging this stuff in, especially with all the negative signs going on. So we have our left-hand side. I'm just going to leave that one alone. On my right-hand side, I still have this negative e to the 2t cosine t. Remember we pulled this negative 2 out, so this is really a positive 2. And then inside this parentheses, I'm going to do the integration by parts of the remaining integral, which is u times v e to the 2t sine t minus the integral v du, so 2e to the 2t sine t dt. Okay, so just to clean this up a little bit, still have the left-hand side, just going to copy that one down. All right, on the right-hand side, just copying this one down, negative e to the 2t cosine t. This 2 is going to distribute here, so plus 2e to the 2t sine t. And then just minus, the 2 does distribute here, and I'm going to pull the 2 out of the integral, so minus 4 integral of e to the 2t sine of t dt. Okay, so now is the trick that we have when we do these special integration by parts. We have an integral e to the 2t sine t dt on the left with the coefficient of 1. We have an integral e to the 2t sine t dt on the right with the coefficient of negative 4. I'm going to add this entire term over to the left-hand side. And when I add 4 of this integral to 1 of that integral, we get 5 of that integral, e to the 2t sine of t dt. On the right-hand side, we still have those remaining terms, the negative e to the 2t cosine t plus the 2e to the 2t sine t. All right, last step will just be dividing the 5 over. So our final answer here for this integral is that this integral, e to the 2t sine of t dt, is negative 1/5 e to the 2t cosine t plus 2/5 e to the 2t sine of t. Okay, good. So just going and scrolling back up here, remember we needed this integral. We're going to throw a square root of 2 in the front, and we're also going to evaluate the antiderivative from 0 to pi. The antiderivative is this stuff here on the right-hand side. So remember, just to make some notes here, we have to multiply by that square root of 2 and evaluate from 0 to pi. Okay, so multiplying both of these by square root of 2, I'll just put that on the outside. And then let's do the evaluations on the inside. If I plug pi into these two terms, cosine of pi is negative 1. So that's going to cancel out with this negative, and we're going to get a positive 1/5. And then plugging pi in for that t, we get e to the 2 pi. If I plug pi into the second term, sine of pi is just 0, so that just disappears. That's going to be minus plugging 0 into these terms. If I plug 0 into cosine, I just get a positive 1. So it's going to be a negative 1/5 e to the 0, which is just negative 1/5. But it was already minus, so those minuses cancel out, and we get a positive 1/5 here. If I plug 0 into sine, I just get 0. All right, so this here is what we were trying to solve for to begin with. So just to remind you, this thing that we just solved for was the integral from 0 to pi of that square root 2 e to the 2t sine of t dt. And then an even better way of thinking about that is remember that this was our m sub, I forget which one we were solving for, m sub x. All right, so this is my m sub x, the moment about the x-axis, which means that we can go ahead and find our y bar. So remember the y bar is the moment sub x divided by the total mass, which for us is going to be this thing right here. So the square root of 2, 1/5 e to the 2 pi plus 1/5. And that's going to be divided by the total mass, which we did find a little bit ago. This was the total mass, square root 2 e to the pi minus 1. So we're dividing that by square root 2 e to the pi minus 1. Nice. So you can see that the square root of 2's are just going to cancel out. We can also multiply top and bottom by 5 to get rid of those exponents. So here we're going to have e to the 2 pi plus 1 up top, and then just a 5 times e to the pi minus 1 on the bottom. I don't think we can simplify that down any more than it already is. Let's go to the answer here and just double check we got the right thing. And we do, right? So remember we were finding the y bar. So y bar, e to the 2 pi plus 1 over 5 e to the pi minus 1. E to the 2 pi plus 1 over 5 e to the pi minus 1. Okay, so that was just to find the y coordinate of the center of mass. Remember, you also have to find the x coordinate of the center of mass, which you get by doing m sub y. So m sub y is the other way around. So it's going to be an extremely similar integral to the one that you just did up here, but it's going to have a cosine instead. But just follow the same steps with this integration by parts stuff, and you should get it to work out to be very, very similar. Just to show you what the final answer is in case you're really stuck, this is kind of what you're shooting for here after you divide by the total mass to get the x bar. Okay, I hope that helped.